Okay, let's make another video. This is WebWork 6, question 6. It asks you to determine the Thevenin equivalent, Norton equivalent, as well as the equivalent resistance. So let's do part A first. So to determine the Thevenin equivalent, I need to have an open circuit between A and B. Okay, so it's a plus referenced on top. So basically we're asking for the voltage difference for the voltage at A minus the voltage at B. Okay, so to establish that, it's easiest to do a nodal analysis. Just remember when you try to find Thevenin equivalent, you use nodal analysis because it directly gives you the voltage difference. And when you're doing the Norton equivalent, you do a mesh analysis because it just directly gives you a current. So first, let's analyze how many nodes are in the circuit. From the first glance, I can see 3 nodes, but for the sake of clarity, just color them first. I say it's for the sake of clarity, but actually like coloring these nodes is like the most enjoyable part of nodal analysis for me. This is what I'm going to call the ground node. And here is another node. Now let's name them. The ground node is just going to be connected to the ground, so it will have a reference voltage of 0 volts. So we have V1 here and V2 here. Okay, the first thing I noticed is that there is a voltage source between V1 and V2, and since neither of which are ground nodes, which is probably my mistake since I labeled the one on the bottom to be the ground node, it will probably be easier to label the one on the right, label A2 as the ground node, but who cares? So if a voltage source is between 2 nodes, neither of which are ground nodes, we do a super node for the nodal analysis, and we have to write down an additional equation to describe the difference between these 2 nodes. So here I have V1 minus V2 equals to 5Ix. And we realize there is a dependent, the current here, and it's around the resistor that's 250 omega. Okay, so I know that Ix equals to the difference between V1 and the ground node, which is just V1 over 250. Okay, now the only thing I need to do is have a supernode analysis between V1 and V2. In this case, I have a current flowing out here, a current going in here, and current, I'm just gonna define it as going out since it's V2 is higher than the ground node. It's by convention, but you don't actually have to do it. Okay, so for our supernode, I'm gonna circle it for the sake of clarity. Beautiful. The current exiting, we have Ix plus this one, which is V2 over 7.5K omega equals to the current entering, which equals to 0.1 amperes. Okay, so now we have 3 unknowns, V1, V2, and Ix, and we have 3 equations, so we can just solve that and get our V1 and V2. And we notice that the Thevenin equivalent is just V2 minus 0, because it's the difference between here and here, right? Okay, so our answer here would be V2, given that we have solved this matrix. I'm gonna post the exact answer later, but it seems like kind of a waste of time to try and solve this. Okay, now we can try to solve part B. Just gonna erase all this first. So to determine the Norton equivalent, I need to have a closed circuit here. by convention, it's floating from here to here. Okay. This is part A, part B. And for determining the Norton equivalent, we need to do mesh analysis. So first, let's identify all of the meshes. Let's do, here I already know it's IX, so I'm just going to call this IX. And here, I1, I2. Okay, and now we can see there is still a current source between IX and I2. Why is this? I'm so sorry. There's a current source between I1 and IX. So we have to do a super mesh between these two meshes and extract information from the current source. So here we have, this is towards actually IX plus I1 equals to 0.1 amperes. And the super mesh for I and X would be this big mesh. And let's just start from here in this direction. So we have 250 ohm times negative IX. So apparently I have picked not so pretty direction. Plus 5IX plus 7.5 K times I1 minus I2 equals to 0. Okay, then we have the mesh on the further right, mesh 2. And this gives us 7.5 K I2 minus I1 equals to 0. Here we have, again, 3 equations and 3 unknowns, which will help us solve for the whole circuit. And in this case, this is I Norton here. It's going to be equal to I2. So IN equal to I2. Okay, so when we have both the Thevenin equivalent and the Norton equivalent, our R equivalent is just V Thevenin over IN. So in the case where you have dependent sources in your circuit, this is probably the best way you can calculate R equivalent. That's it for this question. Let me know if you guys have any concerns.